Hey, welcome to The Explainer. Today, we're going to dive into a kind of hidden language, one that shapes our entire world. From the sound of your voice to a signal from a distant star. It's the language of signals, and we're about to see how one simple change in perspective makes it all click into place.
So think about it for a second. I mean, on the surface, they seem totally different, right? One is sound, another is financial data, and the last one is an electromagnetic pulse bouncing off something. But they're all connected by one single fundamental idea.
And there it is. That's the simple answer. Each one is just a stream of information that changes over time, or sometimes over space. But what does that really mean?
At its core, a signal is just an ordered set of data. And when you plot that data against time, you usually get these really complex, wavy lines that look, well, let's be honest, kind of chaotic.
So that's the big question, right? How do you look at two of these crazy squiggles and know if they're similar or if they're completely unrelated? Just staring at a graph, it's clumsy. There has to be a better, more elegant way to see them. And the answer is a huge yes. This is it. This is the big idea, the mental shift that unlocks everything. Instead of seeing a function spread out over time, imagine you could take that entire signal, that whole wavy line, and represent it as a single object, a single arrow in a vast abstract space.
Yeah, most of us probably remember vectors from physics class, right? They're just arrows, they have a length, and they have a direction. But the real magic happens when we apply this simple, geometric idea to something as complicated as a signal. Okay, so think about it. If two vectors are similar, they're basically pointing in the same direction. The angle between them is super small. Well, in the world of signals, that geometric angle has a direct mathematical partner. It's called correlation. Two signals that are highly correlated are just like two vectors pointing in almost the exact same direction.
And what about the opposite? Vectors at a perfect 90-degree angle? We call those orthogonal, and they are completely independent. One has absolutely zero influence on the other. It's the exact same concept for signals. Two signals are orthogonal if they are totally unrelated, meaning their correlation is zero. They are complete strangers to each other.
So we've just translated this messy, chaotic world of squiggly lines into the clean, super intuitive world of geometry. And let me tell you, this isn't just some neat party trick. This is, well, it's pretty much the foundation of all modern signal processing.
Think about it like this. You have a vector in 3D space. How do you describe where it is? You just break it down into its x, y, and z parts, right? Those axes, they're your orthogonal building blocks. We can do the exact same thing with any signal. Any complex signal can be perfectly described as just a sum of simpler, mutually orthogonal signals. So what are these fundamental building blocks for signals? Turns out they're just simple sine and cosine waves of different frequencies. It's like how you can make any color you can imagine from a recipe of red, green, and blue light. You can make any signal from a specific recipe of sine waves. And that recipe has a name, the Fourier transform. And this is what that recipe looks like. It's called the frequency spectrum. Each of these bars tells you exactly how much of a specific frequency, a specific sine wave, you need to add to the mix to build your original complex signal. It's the signal's unique DNA, its fingerprint. This is so fundamental that for engineers who live and breathe this stuff, it just becomes second nature. They're not even seeing the wavy line anymore. They're seeing the frequency recipe. It's the language they speak. Okay, this is where it gets really practical and really cool. Once you have the recipe for a signal, you're the chef. You're in control. You can start tweaking the ingredients to change the whole dish. So in the engineering world, anything that messes with a signal is called a system, or more often, a filter. And all a filter really does is change a signal's frequency recipe. That's it. It might turn some frequencies up, turn others down, maybe even delay them a bit. So what if you don't want to change the signal? What if you want it to pass through a system perfectly, with zero distortion? Well, you've got to follow two simple rules. First, you have to treat all the frequencies equally. Don't boost the highs more than the lows. And second, you have to make sure every frequency gets through at the same speed. If you delay some parts more than others, the whole signal gets smeared out.
Conceptually, an ideal filter is easy to imagine.
It's like a perfect brick wall. Certain frequencies walk right through, no problem. Everything else? Bam! Hits the wall, stopped cold. Simple, right? But, yeah, as it turns out, a filter this perfect is physically impossible to actually build.
So real-world filters, like the common Butterworth filter, are a compromise. Instead of that sharp, perfect cliff, you get this smooth, gradual slope. They get close to the ideal for sure, but there's always a trade-off between how sharp that cutoff is and how the filter performs in other ways.
Okay, so far we've been talking about analyzing signals, shaping them. But this whole geometric way of thinking has another, honestly even more amazing application: finding a tiny little signal when it's buried in a giant mountain of noise. Let's take a radar system. It sends out a pulse with a very specific shape, its own unique vector signature. Then it just listens. And what comes back is mostly random static, right? But maybe, just maybe, a faint echo of that original pulse is hiding in there. The system's job is to calculate the correlation, and remember, that's just the angle between what it received and the signature it's looking for.
If that echo is in there, the angle will be tiny. You get a high correlation. If it's just noise, the angle's going to be close to 90 degrees. And why does that work? Because random noise is, on average, totally unrelated. It's orthogonal to the one specific signature we're looking for. It's like shouting your name in a crowded room. Most of the sound is just random chatter, but your friend's ear is tuned to find your specific vocal signature.
And that's really the big takeaway here. Whether we're talking about your Wi-Fi, your cell phone, a GPS signal, the tech works because of this powerful shift in thinking. We stopped seeing a messy waveform and started seeing a single point, a single vector, in this huge geometric universe we call signal space. Thinking of signals as vectors literally unlocked our modern digital world. It kind of makes you wonder, doesn't it? What other huge, complex problems are out there, just waiting for the right analogy, the right change in perspective, to suddenly become simple?